Merry Christmas, Internet, and welcome to snowy Fairfield County, Ohio, which is currently under a level 2 snow emergency. I know you probably can't see me very well in the video, but with this festive background, I just couldn't resist. In any case, I am Matt Buyak, and in this video, we'll be taking a look at the 30th problem from the Project Euler Problem Archive. Now, this problem asks us to find all of the integers for which the sum of the fifth powers of their digits is equal to the number itself. Now, the strategy we're going to use for solving this problem is pretty straightforward. We're just going to start at 1 and try numbers until we find all of the solutions. A few notes. We're not actually going to be starting at 1 because 1 is specifically excluded. And in fact, the problem statement indicates that only integers with 2 or more digits should be considered. The other thing to note is that we're going to need an upper bound, some point at which to end our search. We can't actually try all of the integers. And so determining that upper bound is going to be our first order of business. So with that in mind, let's get into it. As usual, we'll copy our template directory to make our problem directory, and we'll open our analysis file. Okay, so we first want to note that if we take the largest integer with d digits and we take the fifth power of those digits and sum them, we're going to get some upper bound for the largest possible sum of fifth powers. And in particular, the upper bound for sum of fifth powers of digits for a number of d digits is d times 9 to the fifth. And that's just because 9 is the largest digit that we can have. We'll also note that the smallest integer with d digits is just 10 to the d minus 1. And we can see that one of these is obviously going to grow much faster than the other. And so after some point, it will be impossible for the sum of the fifth powers of the digits to be equal to the number itself. And it doesn't take that much trial and error to determine that that will happen when d goes from 6 to 7. And so if we do 6 times 9 to the fifth, we'll see that we get 354,294, a 6-digit number, so obviously that works just fine. But then if we do 7 times 9 to the fifth, then we also get a 6-digit number, which is obviously smaller than the smallest 7-digit number. Now, we could formally prove using induction that this will always be the case for larger numbers, but I think it's not too difficult to see that based on these two expressions. So we'll just note that our upper bound here is that value. Okay, so now let's get into our solution proper. Open up our main.cpp, and we'll say const uint32t, n is equal to that value. That's going to be our upper bound. We're also going to need an index I and a sum, which is going to start at 0. And as I indicated, we're just going to start at 10, the smallest 2-digit number, and try integers until we get to our upper bound. So let's say for I equals 10, I less than or equal to n, increment I. and then we'll say if is solution I, sum plus equals I. And then we just need to print our solution. And that's just going to be the sum. In case you didn't catch it, going back to the problem description, it asks us to sum all the numbers which meet our criteria, and that's going to be our final answer. And so that's what we're doing in our code here. So now we just need to implement this helper function, is solution. And so we'll say bool is solution, uint32t n. So this is also going to be fairly straightforward. Just take our integer, extract its digits, take their fifth powers, sum them, and check to see if we get back our original number. And so we're going to have uint32t. We're going to have an index I. Digit is going to be the current digit. And then sum is going to be our sum. We'll also need a buffer to hold the digits of our integer. Now, the reason that I've used 7 here is that our largest possible number is going to be 6 digits, and when storing a string in C, you need 1 character for the terminating 0. We're going to use the function sprintf to convert our integer into a string of digits. If you want more information about that function, you can just go to CPP reference here. It has all of the details. Okay, so let's do len equals sprintf. We're writing into the buffer a single unsigned integer, and that's going to be n. We will need to declare len. That's just going to be the number of digits that were written. And then we'll just iterate from I equals 0, I less than len, increment I, and we'll extract that digit from our buffer. So we'll say digit equals buffer I minus 0. Excuse me, 0. This is subtracting the ASCII code for 0 to get the actual digit. ASCII is just the encoding scheme used for characters and strings. Okay, so then once we have our digit, we can say sum plus equals digit times digit times digit times digit times digit. And we can say if n is equal to sum, or excuse me, we'll just say return n is equal to sum. Okay, so that should be good. Let's go back to our shell, make, go into our problem directory and make. Looks like I am missing a semicolon. And here we have our answer, 443,839. So let's go back to the archive here. And we'll see that that is, in fact, our solution. So I just want to thank you for joining me on this wonderful Christmas morning. I hope you're having an excellent holiday, and I look forward to seeing you in the next video.